Today we will study about Faraday's laws of electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. For this, we wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. We connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary, as can be seen from the figure. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, the current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The pointer of the galvanometer deflects towards the left when the south pole of the magnet is moved towards the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the right. The deflection increases if the magnet is moved with greater velocity. The velocity is indicated by the small and big arrows below the magnet in the figure. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. When the magnet is pushed towards the coil so that the magnetic field inside the coil is increasing and the current is in the anti-clockwise direction so as to offset the effect due to increase in the magnetic field. But when the magnet is pushed away from the coil so that the magnetic field inside the coil is decreasing and the current is in the clockwise direction so as to offset the effect due to decrease in the magnetic field. So we observe that the direction of deflection in the galvanometer is reversed if the direction of motion is reversed. The factors leading to increased current in the coil are by using a strong magnet. Second, increasing the motion of the magnet. Third, increasing the area or the number of turns of the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant, so the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes current to flow through it. Now we are summarizing the results of the Faraday's experiments. When the magnet is at rest, there is no deflection in the galvanometer. This you can observe in the video which is shown in this slide. When the magnet moves towards the coil, deflection in the galvanometer is in one direction. When the magnet is held stationary at the same position near the coil, no deflection in the galvanometer. When the magnet moves away from the coil, the deflection in the galvanometer but in opposite direction. When the magnet is held stationary at the same position away from the coil, there is no deflection in the galvanometer. So based on his experiments, Faraday formulated two laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. John Ambrose Fleming gave two rules to determine the direction of motion or the direction of induced current. While the Fleming's left-hand rule is for electric motors, the right-hand rule is for generators. According to Fleming's right-hand rule, if the thumb, the forefinger and the middle finger of the right hand are stretched perpendicular to each other, and if thumb represents the direction of movement of the conductor, forefinger represents the direction of the magnetic field, then the middle finger represents the direction of the induced current. Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it, as can be seen from the diagram. When the north pole of the magnet is moved towards the coil, end of the coil becomes north pole, and when the north pole of the magnet is moved away from the coil, the end of the coil becomes south pole. So according to Lenz's law, when magnet is inserted into the solenoid, a north pole will be induced on the right side of the coil to oppose the incoming north pole. By right-hand grip rule, the induced current will flow anti-clockwise so that the pointer deflects to the right. According to Lenz's law, when magnet is withdrawn from the solenoid, a south pole will be induced on the right side of the coil to oppose the outgoing north pole. By right-hand grip rule, the induced current will flow clockwise so that the pointer deflects to the left. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. Lenz's law also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is constant. Lenz's law is based on Faraday's law of induction. According to Faraday's law, EMF is given by minus n delta phi by delta t, where n is the number of turns of the coil, phi is equal to Ba, and that is called magnetic flux, where B is external magnetic field and A is area of the coil. The minus sign denotes Lenz's law. EMF is the term for the voltage generated or induced. A coil of wire moving into a magnetic field is one example of an EMF generated according to Faraday's law. The current induced will create a magnetic field which opposes the buildup of magnetic field in the coil. Now we will summarize whatever we have studied in graphics form. First we have seen magnetic flux phi, then we have seen the Faraday's experiment from which came Faraday's law, and then came Lenz's law. Now let us see Lenz's law in a straight conductor. Lenz's law states that when an EMF is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it. Now let us summarize whatever we have studied. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant, so a galvanometer shows no deflection. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. According to Fleming's right-hand rule, if the thumb, the forefinger and the middle finger of right hand are stretched perpendicular to each other, then the thumb represents the direction of movement of the conductor, the forefinger represents the direction of magnetic field, and the middle finger represents direction of induced current. Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it. Let us see some fun with electromagnetic induction. Thank you for watching this video. Please do not forget to subscribe to the channel and to give your valuable comments.